Welcome back, ladies and gentlemen, to another exciting episode of Dave Does Math from Home. Today we are talking about section 8.3. We are doing trigonometric integrals. This isn't a great name for the section because we've been doing trig integrals for a while. We know how to integrate sine and cosine. We've done like integration by parts things with trig, and we've done integration by substitution stuff with trig. So we've been doing trig integrals for a while, but this section is about a very specific kind of trig integral that we're going to go pretty deep into. And there's not really a great way to describe that kind of trig integral, so we're just going to call these trig integrals. We're going to be fine with that. So, trig integrals. Let's start with a quick review. Let's do the integral of sine squared x cosine x dx, and while we're at it, let's also do the integral of cosine cubed x times sine x dx. These are integrals that we can do. Both of these integrals involve trig functions raised to powers. We have sine squared here, we have cosine cubed here. Anytime we're in that kind of situation, we should be looking at that and thinking, this is a compound function, this is a compound function, I bet I need to use substitution here. And that's correct. You do need to use substitution here. Here the inside is sine x, outside is the blob squared, and the other is cosine x dx. So we'll set w equal to the sine of x, and then dw will be cosine x dx, which matches this perfectly. So we can rewrite this as the integral of w squared dw, and then that's just w cubed. That's w cubed plus c over 3. So this is sine cubed x over 3 plus c. Pretty straightforward stuff. This one's going to go almost exactly the same, except the derivative of cosine is going to be negative sine. So I need that to be negative, and I'm going to put a negative up front to balance it. And then when I do the substitution, I'm going to skip some steps. When you do the substitution, you should get cosine negative 1/4 cosine to the 4th x plus c. If you want the steps here, then pause the video. Do it. It's pretty straightforward. I believe in you. So the thing I want to say about these two examples is both of these examples use integration by substitution, and they both work because next to this trig function to a power, this composite power function trig function combo, next to that in each of these we have a single copy of the other trig function that we can use as the other when we do this substitution. Hopefully you did pause the video and did out the details on this. The other function here was sine x dx, and the derivative of cosine x is negative sine. So we have this, we can use that as the other. That's what lets us use integration by substitution on these things, and that is the goal. Any number of sines, any number of cosines, doesn't matter. As long as you have exactly one of the other piece, you can do this substitution technique. So this is old news. This is stuff that we've done before. The exciting new stuff we're going to get to in this section is how we're going to handle cases where we don't have exactly one of the other piece. So in the last two examples, we had exactly one cosine that we could use as the other, or exactly one sine that we could use as the other. Here we have 3 cosines and 4 sines. That's not particularly helpful for us. If we want to do substitution here, we need to have exactly one of these pieces. So most of this section is about manipulating this to get rid of some things. We want exactly one cosine or exactly one sine. And there is a really, really easy technique we can use to sort of transform sines or cosines into their other ones. So we can transform cosines into sines, or we can transform sines into cosines, but it only works in pairs. We can transfer sine squareds into cosine squareds, or vice versa. We can transform cosine squareds into sine squareds, but they have to be in pairs. So because we're going to be switching these things pairwise, we want to be doing that transformation on whichever one of these things is odd. So if we did it to the sine function here, if we took these 4 sines and split it up into 2 different chunks that were each sine squared, we could transform each of those sine squared pieces into cosine. And then we would have nothing but cosines. And that would be profoundly useless for us, because we can't do substitution on nothing but cosines unless there's a sine in there somewhere. So we're going to do this transformation to the cosine piece, because if we transform 2 of these cosines into sines, then there'll just be 1 cosine left, and having exactly one of those things left is the goal. That's what we want out of this section. Transforming this until there's exactly 1 cosine or exactly 1 sine, and then we can use that piece as the other in our integration by substitution, and then everything works out nicely. So that's the goal. Let's talk now about how this transformation works. First, I'm just going to split the 3 cosines into 1 cosine and 2 cosines, and then here's the 4 sines. So 4 sines stayed the same, dx stayed the same. All I've done so far is transform my cosine cubed into cosine and cosine squared. The way that we're going to transform these cosine squareds into sines is using the Pythagorean identity. This is, I think I mentioned a couple of videos ago, we were talking about the half angle formulas, and I sort of had to run off screen to double check that I was using them right, because I never keep them memorized. There's exactly one trig identity that I do keep memorized, and it's the Pythagorean identity. Basically, it's sine squared x plus cosine squared x equals 1. And this comes from right triangles on the unit circle. On the unit circle, this distance, the radius is 1. This is the sine, this is the cosine. They always make a right triangle. A squared plus b squared equals c squared. This is the Pythagorean theorem, just written using sines and cosines on the unit circle. That's why I keep it memorized, because it's really, really easy to keep memorized. Like, the Pythagorean theorem is just etched into my skull, like it's impossible to forget. And this is the same thing, so it kind of piggybacks off that space in my head. This is not the form in which we're going to use it. This thing can be transformed if you subtract sine squared from both sides. You get cosine squared x equals 1 minus sine squared x. This is the form that we're going to be using in this example here to substitute out this cosine into 1 minus sine squared. This is I was just talking earlier about the transformation. We were going to transform cosine squareds into sine squareds. This is it. And you could also go backwards if you're doing a different problem where you need to transform the sines. Then you can subtract cosine squared from both sides, and you have sine squared is 1 minus cosine squared. That also is the Pythagorean identity, and that also works. But here we're going to do the cosine version, transforming cosines into sines. that's going to look like the integral. Cosine x, this stays there. I need to leave this alone. That's going to be the other when I do integration by substitution. This piece is going to be 1 minus sine squared x. It's still being multiplied by sine to the 4th x. And there's a dx here. So I'm going to take this sine to the 4th x and I'm going to distribute it in here. To try and simplify this a little bit. The cosine I'm not going to distribute. I want the cosine to stay separate because I want this to be the other function when I do this integral. This is I'm just going to write as sine to the 4th x minus sine to the 6th x dx. So once you have this piece isolated as it's just the one copy of one of these guys, leave it alone. Don't distribute that in there, just have it be separate. That's the other piece. Well, that and the dx are the other pieces. Leave them alone. From here, I can start doing the integration by substitution, but I'm going to need more room, so I'm going to erase this top stuff. So the inside is always going to be, for these problems, inside should always be a trig function. Outside's going to get kind of messy sometimes. We'll talk about that. The other is cosine by design. We definitely wanted it to do that. So if the inside is sine and the other is the cosine, the outside has to be the rest of all of this business. The outside is everything that is happening to the sine function. So I don't know if we've talked about this before. I can't remember if I included this in another video, but I call this the double blob technique. Usually when we do these outside functions, it's just something's happening to the blob. But here we have two sines. We need two blobs. The outside function here is blob to the 4th minus blob to the 6th. This is the double blob technique. Some of the problems you'll encounter in this section will require a triple blob technique. So be prepared to deal with that. Conceptually, it still works exactly the same as regular integration by substitution. We're not really changing anything. We're just using two blobs for the outside. So hopefully that is not a huge conceptual hurdle. Plus, it's just fun to say double blob technique. So, like, practice this so that you can tell your friends that in calculus today you learned the double blob technique. It's a very important sentence to say. You can trust me. The rest of integration by substitution goes like normal. We're going to set w equal to the inside. And then we're going to take the derivative, and that will be a cosine. And it will perfectly match the other that we already have here. So we're going to rewrite this as the integral of, this is dw, this is w to the 4th, minus w to the 6th dw. And that's w to the 5th over 5, minus w to the 7th over 7, plus c. And then we just swap those back out for signs, and we have sine to the 5th x over 5, sorry, not plus, minus sine to the 7th x over 7 plus c. And that is, the original is long gone already. This is the integral of, what did we start with? Cosine cubed sine to the 4th? Yeah. Okay. We started with cosine cubed sine to the 4th. We end up with this. That's trig substitution. Or not, that's not trig substitution. That's trig integrals, whatever this section is called. Trig integrals. Integrals of weird trigonometric functions that are composite inside of power functions, I think is the better name if it weren't too long. We are at 15 minutes. If I start another example, I will try to rush it and it will not be good. So I'm going to cut this one here. We'll start part 2 of this video series with another example, and then we can start talking about the weird stuff when this technique encounters problems that we have to solve. So stay tuned.